Hello and welcome to our advocate chat talking about diagnostic imaging and radiation safety. I'm Jerry Francor and I chair the Society of Nuclear Medicine and Molecular Imaging Committee on the Patient Advocacy Advisory Board and have served with our guest, Dr. David Mankoff, for several years. I also serve on the Alamo Breast Cancer Foundation Committee for the Advocacy Program during the San Antonio Breast Cancer Symposium. Dr. Mankoff, our guest, is a professor of radiology, vice chair for research in radiology, director of the PET Center at the Perelman School of Medicine at the University of Pennsylvania. He also serves as the associate director for education and training for Penn's Abramson Cancer Center. Dr. Mankoff is a board certified in nuclear medicine, holds a PhD in bioengineering focusing on PET instrumentation. He also is a past member and president of the American Board of Nuclear Medicine, is on the editorial boards of Nuclear Medicine and Biology, Breast Cancer Research, the Journal of Nuclear Medicine, the Breast Journal, and Clinical Cancer Research, and serves as an associate editor for the Journal of Nuclear Medicine and Breast Cancer Research. So let's get started. This is one of my favorite topics as it brings me back to my roots. I started my career in 1973 as an X-ray tech or radiologic technologist, where we actually did everything from radiation therapy, nuclear medicine, as well as general radiography. And I also live in Florida where I'm in the sunshine all the time. So I get asked questions about my exposure to radiation. And I basically tell them I am in radiation constantly from when I worked as my career and in the sun, and that I would be glowing by now if there were any major issues. So Dr. Mankoff, let's get started and go to the questions.
That sounds great. And I just want to say I'm delighted to be participating in this, Jerry. I'm a huge fan of Komen, of San Antonio Breast Cancer, a meeting which I've been actively involved in, the Alamo Foundation, and all of their outreach and advocacy efforts. So thank you for including me. Fire away. Go ahead and irradiate me.
We're going. Will you please speak about the different types of radiation, from general X-rays to radiation therapy and nuclear medicine? Radioisotopes, are they safe? And can you give us some analogies?
Yeah, that's a good broad question. And if you've got a couple of hours and maybe a time for a PhD, we'll go through all of that. In general, when we think about radiation, we think about, we talk about it in this context, we talk about higher energy, sort of more potent forms of the same type of radiation that we get when we have light. So for example, visible light is radiation. It just happens not to be at high enough energy, potent enough to actually cause ionization. When we talk about radiation in the context of diagnostic imaging, radiation therapy, and certain other processes and treatments, we're talking about that same form of energy, but where the individual particles are potent enough that they can actually cause some ionization or changes to the chemicals that they interact with. When that ionization happens with the body, there can be potential consequences from it, especially if it's at high enough intensity and dose to have issues. I want to clarify that when we're talking about diagnostic radiation, either with an X-ray or a CT scan or mammography or radioisotopes in the case of nuclear medicine and PET, we're really talking about very low amounts of radiation that we don't expect to have any physical effects, but may contribute to a long-time risk of secondary processes such as the generation of a cancer. At the far end of that, when we use radiation to treat cancer, we actually count on that radiation having an effect to kill the cancer. And there we're worried a little bit more about making sure that the normal tissues don't have the same side effect. But if we combine this discussion of diagnostic radiation, we're at the level of radiation where there'll be no side effects. And we're really managing, as you did in your introduction, risk versus benefit.
That's a great explanation. What is nuclear medicine?
So nuclear medicine, number one, those to people like you and I that haven't been in the business, those are two words that sound like they shouldn't go together. Together. So nuclear medicine started and still is fundamentally the application of radioisotopes that are generally don't occur in nature very much, that we produce from a reactor or a cyclotron, that are used primarily for diagnosis at relatively low radiation doses, but more recently can also be used for therapy in the form of theranostics, where they provide very, very localized radiation therapy delivered by a radioisotope. We started out as the Society of Nuclear Medicine. We're now the Society of Nuclear Medicine and Molecular Imaging. And part of that is that it's a field that has revolutionized imaging in certain ways, because the use of radioisotopes allows you to image at chemical concentrations of contrast agents that the body simply doesn't know about. And we can image these very, very sensitive procedures that no other modality can image at this point because of that. And I'll go in through some examples as we go through, but nuclear medicine is a very specialized part of this process, where we do something that sounds very creepy, like injecting isotopes into people, but in fact, it's a very powerful and relatively low dose diagnostic technique. And when we turn it towards the therapy end, it can actually be a very, very potent and actually relatively few side effect containing treatment for cancer.
What are the advantages of nuclear medicine and molecular imaging, and how is it used in screening, diagnostics, treatment monitoring, response to therapy, and what all can we learn from it?
Yeah, so the advantages of radioisotope imaging in nuclear medicine, which includes positron emission tomography or PET, is main advantage is the ability to be able to image fundamental molecular biologic processes without perturbing them. Your body's not radioactive, right? So every molecule of radioactivity that we put in your body is contrast. It's something that's not part of your body. So we can use very, very sensitive instrumentation that comes from nuclear physics principles that allows us to detect these very, very small quantities of material and get information on the molecular composition and the behavior of the body and the cancers and other diseases in ways that we couldn't otherwise. It allows us to do that in the whole body at once. So we can look at the full body burden of disease. It allows us to do that over time. And do repeat studies to look for responsive therapy. And it allows us to do that at a relatively low dose. The nuclear medicine itself, under modern conditions that are getting better all the time, actually provides less radiation dose than a fully diagnostic CT does, for example. So it is this very interesting technique that gives you a lot of features that are unique to the use of radio isotopes. I'll come back in a second and talk about some of the limitations. But one of the limitations is that for a variety of reasons, especially in breast cancer, this is not something that has yet been applied to routine screening the way mammography would. And we can talk about that a little bit more, but it has tended to be more in the realm of diagnosis of people with highly suspected or known cancers, and is especially potent in breast cancer for looking at the spread of cancer and looking at how cancers respond to treatment.
Is it used more for those that are in advanced stages or earlier?
I would say that right now, the majority of nuclear medicine studies applied to breast cancer, which include things like bone scans, PET scans, probably the two most common, are used in patients with a little bit more advanced disease because the PET scanner is very good at identifying the pattern of spread in more advanced diseases. It is a very, very efficient way of PET, and to a lesser extent bone, following response to treatment. You know a patient has a number of sites of disease related to the spread of breast cancer through metastases. PET is a very good way of basically having one-stop shopping to try to monitor that disease all at once. So right now, those are the most common applications. There are some earlier stage applications of nuclear medicine. Many patients who have been through breast cancer and had sentinel lymph node mapping know that we use a very, very small amount of radioactivity to identify sentinel lymph nodes. Is probably one of the most robust ways to do that. There are also some techniques that are beginning to look at the breast in specific to help with diagnosis at an early stage, but those are a little less commonly used than some of the applications for more advanced diseases.
Can you discuss how molecular imaging biomarkers are used to personalize treatment now?
Yeah, no, this is my favorite topic. It's something that I've been working on for a while. So just to drop back for a second, when we think about imaging cancer, we think about detecting or diagnosing cancers, and as I mentioned, identifying and detecting sites of spread. That's a really important use of all diagnostic imaging modalities, including nuclear medicine. Nuclear medicine also has another feature because of its ability to measure what I call the biology in the patient, or in vivo biology. It can look at tumor characteristics in a way that the other modalities can't, and it provides information that is complementary to, that adds to the ability for what you can look at under a microscope by taking a small piece of tissue and doing a biopsy and analyzing that. So there are some really exciting applications. One that I've been working on for a long time is the ability not just to tell where the cancer is, but what flavor it is. And in particular, there's now an approved agent in PET that can look to see whether or not breast cancer contains estrogen receptors. And I think many people who are familiar with breast cancer will know that importance, because then it can be used not only to identify disease, but to say, hey, here is somebody who has estrogen receptors at all of the sites of her disease, and we can use this very targeted and reasonably non-toxic hormonal therapy to treat her rather than having to go to chemotherapy. And to me, this process, which has been evolving for 20 years and has come into the mainstream in the last year or two, is a really exciting and very potent use of molecular imaging. So thank you for asking me that question.
Are imaging techniques used in combo, and how have these techniques evolved over the years?
Yeah, we in radiology sometimes think that it's important for us to fight about whose modality is better. MR is better than PET, no, PET's better than MR. And in fact, these fights have largely gone by the wayside. So these days, and this has been going on for about 10 to 15 years, most nuclear medicine devices will be attached to something else. For example, you can't buy a standalone PET machine anymore. It most typically comes as a PET attached to a CT, or in some cases, a PET attached to an MRI. The reason that's helpful is the CT can look at anatomy and knows where things are, know what the structures are. The PET scanner looks at the biology. And when you marry the biology to the structure, you have an incredibly potent technique that can be used for everything from biomarker imaging that I just talked about to actually directing biopsy or helping to guide things like surgery and radiotherapy. A combination of our practice approaches, us coalescing as a group of practitioners, and especially the development of what we call this hybrid technology, has really revolutionized the field, that none of these things stand alone on their own anymore. And we've made it so that it's actually easy to get two of them at the same time.
So is this able, are you able to see like the microenvironment of the tumor itself better and the microenvironment around the tumor?
Yeah, so just to clarify, the spatial resolution of PET is actually one of its limitations. The nature of the way we detect those things means we can't see very, very small structures, much less than maybe, a quarter of an inch or a few centimeters or something like that. So we can't see microscopic stuff on a PET scanner, at least not yet, but we can see the biologic environment around the tumor, which is called the microenvironment. That is becoming increasingly important. So for example, the microenvironment would include what kind of nutrients the tumor is using. Is it using oxygen? Is it getting enough blood flow? Is it using up its oxygen supply? All of this affect tumor behavior. And then more recently, that microenvironment has been taken to be the body's innate immunity microenvironment, the ability of the body to fight off things that are not supposed to be there, like bacteria and viruses, and most recently to leverage that immunity and that microenvironment to treat cancers. And as many folks will know, this has revolutionized the care of, for example, triple negative breast cancers and many other diseases. And PET is very well suited to be able to look at those microenvironments with new and exciting things happening all the time in that field.
What are some of the new emerging technologies and research that are being done, and how do you think it'll benefit patients in the future?
Yeah, I think there are three areas there. One is I started life as an instrumentation physicist. I was actually a director of engineering for a company for a short period of time before I went back to my residency. I was a very scary intern because I hadn't done medicine for a couple of years while I was doing that work, but I beefed up. And there's been a lot of advances, some of them a little bit quiet in the development of nuclear medicine and in particular PET scanners. PET scanners have gotten better and better and better and can give us better images at much lower levels and doses of radioactivity. And we're now able to image things that I think wouldn't have been possible 10 years ago. A very exciting application that we're involved in at Penn in collaboration with UC Davis and a couple of other centers around the world is the ability to image the whole body at once. So we can do body imaging with very low dose very quickly, or we can use that to measure dynamic processes over the whole body at the same time to understand how the tumor interacts with the host in ways that we've never been able to see before. So instrumentation is one of the ways that has moved forward. Secondly, in the process of better living through chemistry, we've developed radiopharmaceuticals that can now image many, many facets of the tumor. Only a few of these have been approved so far, but there's more coming all the time. I mentioned the estrogen receptor for breast cancer. There are other related receptors like progesterone receptor with some really exciting work going on at Washington University, University of Wisconsin, and other places. We now have abilities to look at the microenvironment and the ability of the immune system to react to the tumor in new probes that are coming out. We can look at things like DNA damage, in particular targeted agents. We can use agents that are particularly tuned to cell growth or cell death to be able to look at how effective our treatments have been, not months down the line, but within a day or two in some cases. So that probe is going to drive a lot of what we can do diagnostically. The last area, which has been applied a little bit more to other cancers than breast cancer so far, is what's called theranostics. That's a therapeutic and a diagnostic. And what we can do is when we do a PET scan, we put in an isotope that generates what I like to think of as light, that we can actually image it and find where something is. But we can swap out that isotope to almost an identical chemical and deliver very potent, very localized, and very effective radiotherapy. We're starting to see this have a huge impact on a number of other diseases, such as neuroendocrine tumors, most recently prostate cancer. But I think there's reason to believe that this will be yet another treatment that may be possible and helpful for breast cancer patients in the future. Some of it is done right now for bone metastases, but in the future, I expect this will also be a contributor to the treatment of probably more advanced breast cancer, but could be very potent.
That was sort of my next question. What are some of the new isotopes coming out? And more importantly, with these new isotopes coming out, we're looking for reimbursement. So any ideas or help where we can with legislation on getting these things passed for to be used?
Yeah, and just for the terminology, there's the radioisotopes, and we are using a number of different isotopes, actually. We used to use only fluorine-18, which is a positron emitter, but we now have a number of other isotopes. We also have, just to be a little bit of a grammarian, radiopharmaceuticals, which is what you do with those isotopes. So everything that I just mentioned are things that are in research. There are some approved agents, as I mentioned, the estrogen receptor approved agent. We've been using glucose metabolism imaging for a while. There's some other isotopes that look at other receptors that are less commonly used in breast cancer, such as PSMA and the somatostatin receptor, but may have some application in breast cancer. But there's probably a half a dozen different applications that are targeted to therapy that has been important in breast cancer: progesterone receptor, HER2, immunotherapy, blood flow targets, PARP inhibitors. These are all things that are making their way through investigations. So what can we do to help them out? Number one is a lot of these things are still at the investigational stage and are funded by research from NCI and some of the private foundations, including places like Komen and some of the other organizations. So continue to encourage your Congress people to support this type of research, as it's really having an impact. Once it moves into late phase clinical trials and into actual clinical trials and clinical practice, we then have to convince everybody it's worth spending dollars, and sometimes these things are modestly pricey, to be able to have more precision in our approach to medicine. I think it's going to be an easy sell. You know, some of these drugs that we now use that are these very highly targeted drugs, very potent drugs, but they don't work in every patient. You really need to know that the patient and her tumor is going to have this be available. These drugs are really expensive. And so if we can use these drugs in the patients most likely to benefit, and use PET scans also to help us direct patients away from drugs that they're not going to get any benefit at a very early stage, I think they're going to prove their cost effectiveness very, very quickly. Because it used to be somebody said, hey, I'm going to do a couple $1,000s for a PET scan. That seems like a lot of money. Well, you get a week's worth of drugs and it's way more money than that with many of these agents. And so I think we're in the era where this can actually be not only a very powerful technique, but actually a very cost-effective technique.
A little bit about you now, because I have enjoyed working with you and serving on committees with you. Now you're one of my favorite.
And vice versa.
What led you to become a researcher in breast cancer, and how did you get in the field of nuclear medicine and molecular imaging?
Yeah, let me start with the first one, and then I'll talk about the second one in a second. I was an undergraduate physics major. I did applied nuclear research as an undergraduate, and I worked on an accelerator at Yale, where I did my undergraduate degree. And at the same time, I always had an interest in medicine, had a lot of family encouragement to be a doctor. And so I had a dilemma when I was applying. I didn't know whether to apply for a physics or an applied physics graduate degree or medicine. And when I went on my medical school interviews and they said, why do you want to be a doctor? I was tempted to say, because your applications were due earlier than the applied physics. Fortunately, at a number of medical schools, including Penn, I was able to do both and do it through an MD PhD program where I did my medical training, but also did a PhD in bioengineering and medical physics at that time. So that's how I got to nuclear medicine, was really by having exposure to it as an undergraduate. In my training, and a lot of this happened while I was at the University of Washington doing my nuclear medicine training, and where I was a faculty member for a while in Seattle. A lot of this choice to go into breast cancer happened at that point. I had an interest in cancer, but hadn't really decided what I wanted to do. And a few things happened. One is there was a local environment at that institution that was so collaborative and supportive, including many patients who were willing to take on this experimental imaging that is now standard of care like PET, but wasn't at that point, that it was just a natural draw. The other thing that happened, and where advocacy is very important, is this was the point at where breast cancer was one of the first areas where advocates had such an impact upon funding, noting that many women's cancers were underfunded. And so for somebody starting out like me, who was facing the daunting approach to pulling in grants and getting started, the fact that this was an area of emphasis and the advocates had a lot to do with this made it a very attractive field to go into. So it was a draw into the disease, into the patient population, who I can't tell you how much I've enjoyed working with. And in all honesty, the ability of funding priorities to grease those wheels. So the advocates had a huge role in bringing a cadre of folks of my generation and beyond into that process. And other organizations, including Komen, have continued to recognize that supporting scientists, especially at the boundaries between specialties and in translation, has a huge impact on growing the next generation of researchers. There's a period of time when I was a Komen scholar where I was grateful to Komen for supporting those early investigators at a time when NCI funding was really hard to come by for new investigators. And I sometimes say that Komen and other organizations that supported that probably saved a generation of breast cancer researchers that we would have lost. So it's a probably much longer answer than you had. You'll know better than to ask me that question next time, but I'm really very passionate about having chosen this pathway and the help to which the community has provided for researchers like me, and I only hope that I've been able to give back.
It's really weird because it's like you're reading my mind.
It's our mind meld, you know.
I know. It's because the next question is about advocates. What value do you get from working with advocates, and what advice would you give to an advocate who wants to get involved in the research part of it?
Yeah, and let me give you, again, a really long-winded and complicated question. Number one is, I think advocates, especially the patient advocates that have had a connection to the cancer either personally or through their family, are a really important part of the process to give perspective. And let me give a couple of examples of that. One is the perspective that advocates had in the early institution of dedicated breast cancer funding, that here was a disease that was fixable, but it wasn't getting enough priority. And so I think that's a very important, powerful voice that has caught on with a number of other diseases, and I think has really helped the community and the federal government and other organizations identify that. Another interesting thing, and I'll tell you a story about this, is advocates have now become part of scientific grant review, the NIH is coming around to that, but the Department of Defense and Komen and other organizations were important to that. And I had some early experiences as a physicist and how important that was. So early on, one of the priorities of some of these organizations was to develop new devices for detecting breast cancer better. And you got a group of physicists together and engineers, and a lot of these guys were guys, not gals, but that's getting a little bit better now. And they designed a device, and they'd sit around the table and go, oh my God, this is so cool. This is going to change breast cancer. And the poor advocate, who was usually a woman, would speak up and say, you know, guys, women are not built like that. They're not going to fit into your scanner. And the guys would go, oh yeah, we better go back and change this design. So there have been so many positive impacts on research and its outcome from advocating towards what's important to helping at least formerly overly male crowd figure out how to serve this population. It's really been a very powerful force, and I've really enjoyed getting to know you and many other advocates who have really helped shape the field.
I remember one time on one of the DoD reviews I was doing, something similar happened, and they were talking about, I think it was a coil or something, and I'm sitting there and I'm going, you know, women come in all sizes and all breast sizes, and what you're looking at, if she's an F or a G size,
she ain't gonna make it there. Yeah. You may have been that person that I'm telling this about. We finally connected it. No, I just think that there was this rarefied idea that people were academics and in this privileged point to be able to evaluate it. And as you know from being an advocate, there's a lot of biology and technology in there that you're probably not trained in if you haven't been through ages and ages of school. On the other hand, a fresh perspective coming from somebody who's been through the process and understands it from a different angle it is always useful information.
Is there anything else you would like to address or comment on?
No, the one thing I would like to say is, knowing that a lot of the community that may visualize this video are survivors or people who've been through breast cancer, people who've been touched by it. I just want to say my thanks to the community, because as you can tell, I'm not a spring chicken anymore. And I've really been able to have a very successful career, and I'm really grateful to the many patients and their families that help support the ability and the volunteerism for women to come get these experimental imaging studies, many of which have actually paid off now, but there was no way of knowing that at the time, where they weren't necessarily getting any direct benefit, but they knew this might benefit somebody in the future and might enlighten science a little bit. And I just want to say how grateful I am to the community for allowing me to be part of that and to contributing to what has been, and hopefully will continue to be a very rewarding career in research in breast cancer. So.
Well, I want to thank you so much for an interesting and educational talk. And I always enjoy listening to you speak because you bring
vice
it
versa,
down.
Jerry. Yeah, we're going to have to make this a regular, maybe we can get one of these regular podcasts or something.
Yeah.
This may get cut out of the video, but
yeah, that would be a lot of fun.
Yeah.
But I really want to thank you so much for being our guest and speaking on this topic. And I also want to thank all of you for tuning in and watching. Thank you so much.
Thank you, Jerry. Pleasure to talk to you.